Hi, Tom Cherryholmes here with Errata Online and the FujiNet project. And this is going to be kind of a long video with a lot of technical explanation, but I wanted to show a bit about how the end device works, how it will be used for things like TCP communication, and a bit about where my head is at this particular point in time. Now, as usual, I am winging these videos, so if I say something inaccurately, please feel free to point it out, and I will correct it. Starting off with, let's just go ahead and demonstrate where things are currently right now with the end device. The end device is currently being retrofitted to support TCP communication. That is, when you think about most internet connectivity, that's actually happening over TCP connections, things like the web and whatnot, telnet connections, etc. In order to facilitate this, we have, of course, our resident in handler, which is loaded in via autorun.sys. And once we do that, we can actually load a little test program that I have running here called Server 1. And yes, this is actually a listening server that is running on the Atari that's using FujiNet to open up a listening socket on port 2000 and that we can connect to and send stuff down, and it will display it. Now notice here that we actually have some information that will help us find the device. This is gathered from our status from the status changes that have been made in the last couple of days, so that we can show our internal address, our external address, and the port that we're listening on. At this point, I can then use something like netcat to send this particular text file down the socket that FujiNet is providing, and we should see it on our display. You'll hear that we have various sounds going on in the background here. This is literally because we are polling the SIO device, and we actually can turn them off. In fact, if we go ahead and poke a value of 0 into what's called sound R, that actually stops. So if we go ahead and start up the connection here, we will see our text file come across one record at a time. Now, record in CIO parlance means one line at a time. You can see it's doing quite well. So there we go, with a couple of things that need fixing. Some things that need fixing, particularly with the buffers and stuff, but it's working for the most part. And in fact, if we list the program, you can see that there's not much to it. We can see the first few lines take and display our network information after pulling a status request for both of those pieces of information, opening up the listening socket, waiting for a connection, using again the status registers and the status command to do so, and then finally listening for pending bytes and displaying them on the screen. Pretty straightforward. But how do we get to this point? How do we actually get to something that is this useful? Well, in order for us to actually do that, we actually have to demonstrate a couple of things. Here is a very, very simple layer diagram showing kind of where things sit in terms of I/O inside of the Atari. The lowest level is, of course, SIO for serial I/O devices. This provides the ability to send and receive bits of information in fixed blocks to serial I/O devices. Now, this is important because, like I said here, SIO needs to know how large a particular request is, so it knows how many bytes to expect from the peripheral or how many bytes to send to the peripheral. CIO, in contrast, is character-oriented. It deals with I/O one character at a time. So we have to adjust our thinking to accommodate for this. And typically what this essentially means, for most things, is that for CIO, we have to take and buffer our requests to SIO in nice fixed blocks. Digging into CIO a bit further, we see that CIO is actually where the various devices are implemented. The devices in blue are devices that are part of the operating system ROM. They are there when you turn the computer on, and when you hit the reset button, these devices are reinitialized. The devices in green, conversely, are what are called non-resident handlers. They are not there when the computer is first turned on and must be loaded into the system through some action. In the case of D, this is loaded in through the resident disk handler, DSKINV, to load an operating system, or in the Atari parlance, the file management system, into memory, which hooks in this D device and makes it available for user programs to use. Conversely, the R device is loaded in via an auto-run sys handler, which initiates a type 1 poll which loads the device in. A similar mechanism has to be used for our in device. Finding one of these free slots and inserting our device into this device table. This device table in Atari parlance is actually called the handler table, or HATABs. Digging a bit further, we see that each individual handler is comprised of a number of common abstracted functions. Not all which need to be implemented, but some of them need to be implemented for the base functionality. For example, all devices need to know how to respond to open and close. Devices that you can read from need to implement get. Devices you can write to need to be able to implement put. And it's a good idea to have a status command so you know if the device is actually able to do something meaningful. And of course, the special is the ultimate miscellaneous drawer. It is for any command that falls outside of these particular CIO commands. So in basic parlance, this would be called XIO. The XIO commands essentially funnel down to this yellow box. Digging into one of these commands as an example, they all follow a very common pattern. The user program will send a command to CIOV passing in an IO control block containing the information that my handler needs to get its work done. The handler in the middle does its work and either passes out the output in the A register and passes an error code. Both of these values are passed in every case, and it's expected that if the command is successful, that error is equal to 1. Each thing in the parentheses here corresponds to the individual registers. So the IOCB goes into the X register, error goes into the Y register, and the output from the get goes into the A register. Conversely, for put, if we modify put real quick, let's just take, and for brevity's sake, imagine this is the put command. Well, this changes things just a little bit and means that instead the A register feeds the character to be output. It goes through put, and the resulting error winds up in the Y register. So that's the general flow for all of these. Conversely, special is always assumed to be a sort of procedural command or output command of some sort, typically not expecting input. So special, again, looks more like the... Anyway, that's not really used. So anyway, again, sorry about that. I'm winging this. So knowing that, we can go back to the code and start digging through how all of this starts to work. We start by looking at the ESP side of the firmware, because all of the lowest level bits and pieces that are defined in SIO ultimately wind up here. And you'll notice that we have a whole stack of commands, and the ones that we're really interested in are implemented over here in these functions. We take note of that because as we start digging through the code, you'll see how this all maps back together in just a few moments. So let's go back into the Atari CIO Handler, and let's start at main. We can see here, this is literally where it starts. And the first thing that we do is we build a little device handler table, which provides pointers to every single one of the functions that you saw before. These point to our functions that we need to call. And in fact, if you read the Atari technical manuals, they say that it needs to point to the address -1. So we make that correction here. We then take and iterate through the handler table to take and find the next available entry, inject our handler into the slot, display any welcome and or error messages, and finally, once everything is set up, we adjust memlow appropriately. Since this is a prototype, I am adjusting memlow to the bottom of where I know this will sit in memory. I know this because if we look here, we can see that the start address of our program starts here at 2000. And if we look at the map for what's generated, we can see that the most segment ends at 29B7. So it's a good safe bet to set memlow to this so that DOS or something else that's loaded doesn't clobber our program. Moving on, now we actually get into the meat of the program. And let's look at the open command, for example. Now you'll see right here that we have an underscore in front of this function here, and you're thinking, well, that's not CIO open. That wasn't what it looked like over here. What's going on? CIO open, CIO close. Is there some extra magic afoot? Well, yeah, there actually is. And if we look in another file called CIO stubs, we can see some extra magic happening. Recall that in our previous diagram that CIO expects the particular parameters to be in specific registers. The return value in the accumulator, the Y value in the error register, etc. So we put these things in the right place. We call our C function, and since the C compiler automatically adds an underscore, we have to take and do 2 of them here for any C functions. And same for variables. We call our C function, we push our return values into the appropriate places, and then we return. So bringing us back here, we see our CIO open function here. We go ahead and save our aux1 and aux2 values for safekeeping. We need them for later for various different things, to know whether or not certain things are legal. If we only open an end device for read, we don't want to be able to accept write commands, or vice versa. If we open it for update, we want to be able to handle read and write commands. If the socket was opened for listening, we want to be able to keep track of that as well, and so on. And those things wind up in these variables for aux1 and aux2 save so that we can reference them later. Now, you've heard reference from me from moment to moment here talking about certain things like IOCBs. IOCBs are, you can think of them as file handles for CIO, and they are individual I/O channel descriptors for things that you do in CIO. For telling CIO something to do, what type of I/O operation it is, what parameters you want to pass in the aux bytes. Is there a buffer associated with this operation? If there is, how big is the buffer? What unit number or drive number is associated with this particular IOCB request? And so on. As a convenience measure, CIOV also takes and makes a copy of the IOCB that's being used and puts it up into 0 page for us, for our handler to conveniently access, so that we don't have to figure out which IOCB called us. And inside that particular structure, we will find all sorts of goodies. And now notice here I'm using C as an example here because it's a nice middle ground for a symbolic high-level language. If anybody wants to provide similar examples, please feel free to do so. If we look in one of our header files here, we'll actually find the structure of an IOCB. And this is exactly how it's laid out in memory, too. There are 8 of these. So to have everything that you need for a particular I/O request in CIO to happen, including a few auxiliary bytes, which are normally not used, but are provided in case you need them. So in the case of open here, what we're basically doing is saving our aux values for later, and then immediately calling SIOV to do the open. Now this creates an SIO request, which if we go into SIO, do I have, let's see, SIOV, SIO call, yes. We can see our DCB being filled here and calling SIOV, which basically just makes sure that SIO is called. The reason that it's over here by itself is because assembler files are not messed with by the C optimizer. So, with that, we return the value back into dstatus and return. We could use it, but I'm not using it at this particular point in time and just returning success for now. Error code 1 is success. Clear the RX and TX buffers, get everything set up, and there we go. Then there's status. You'll see a similar pattern. Since there's not really much at stake happening here and we're not having to buffer requests, this literally just calls an SIO request for our S. Now notice here, I'm actually explicitly passing through the aux1 and aux2 values that are passed to the status command. This is literally so that if you just use a standard status command, those values will be 0 and we'll get the typical status output that you get, number of bytes waiting, the connection status, etc. But if you set a different aux value, such as 1 through 5, you'll get all sorts of extended status information, like your internal and external IP addresses. We then take and, as part of our return value, we go ahead and return back. Yeah, this isn't really used by BASIC, for example, but we return it anyway. And since status, the variable that goes into status is error, this will return the result of that status command. So, if we dig conversely, let's go here and go back in here and look at here in our command table. You saw this for our status, and if we go look at it, we'll see that for most status requests, aux1 equals 0, then we return various interesting bits of information on our status, ship that off to the computer, we're done. Otherwise, if aux is something else, then we return that interesting piece of information, such as the external IP, which we get here from ICANN has IP, or the internal IP, gateway, DNS, etc., which we get from FujiNet itself. So that's the implementation of the status command. So far, nothing too far out of the ordinary. If we look at CIO close, again, similar pattern. We immediately send a close request. And then, since we're not really expecting or needing anything, it has no payload. And we go ahead and send in the saved values anyway in case we need them. We set everything to 0, and then we're done. Where it starts to get interesting is with CIO get. This allows you to get a single character from the peripheral and return it back to the computer. Now, if we look at Atari I/O, we'll see that there are a number of get commands, and in fact, there are 2 of them. Get record, which is basically equivalent to input number 1, comma a string, line-oriented input, and get character, which means get 1 character at a time, or if you pass in a buffer with a buffer length, get a number of characters at a time, each one at a time. We go ahead and we need CIO status just in case, but we'll start to see here, we check to see if our buffer has anything in it. If not, we immediately return an end of file condition. Or if the client is disconnected, we return an end of file condition, error 136. If for some reason our buffer is empty, then we do a TCP read for the number of bytes that are actually waiting in our buffer, which we got from our status here, which is one of the reasons why we call our status here. We set the receive pointer up, and then we go ahead and figure out, since getRec and getChar share common functionality, all I do is check to see if this bit is set, and if so, it's a getRec, and in this case, we convert the character return line feeds to EOL if they're there, using a skip character technique so that we can differentiate between just having a carriage return, just having a line feed, or having a carriage return and a line feed. Regardless of which, translate that. But you see, the only difference between getChar and getRec at this point is literally checking for the end of line, because getRecord is expecting an EOL character. If it doesn't get one, it will keep reading, and it will overflow its buffer, and you will get an error 137 back. So we have to prevent that. Otherwise, regardless of which, we send the next character in the buffer. Now this is worth noting because this function is called once for every single character that needs to be sent. You might think this is very inefficient. It is. And that is actually why the disk handler implements, in Atari DOS, for example, implements what is called burst mode. Recall that an IOCB can specify a buffer and the length of that buffer. You can have code that checks to see if those things are passed in, and if so, what you do instead is you do all of your I/O operations at once, save for the very last byte that you need to fetch. Put all of that in the target buffer, and then adjust the buffer length and the buffer position so that you're at the very last character of the file, of the buffer, and then do the very last, and then let CIO do the very last, and then let CIO do the very last operation. That will speed things up considerably, and I still have yet to implement that, but it will be implemented, which will speed things up a bunch. So that's CIO get. Conversely, CIO put has to deal with the fact that we need to buffer our put requests so that we don't overload SIO too much. The current behavior for this is currently, if for whatever reason we see an end of line character, then we immediately add the carriage return and line feed and then put a flush. Otherwise, we simply take and fill up the next element in the buffer. This does mean that an XIO command needs to be added to take and flush the buffer out. Conversely, closing the CIO channel should also flush the buffer. I have yet to actually implement that too. That needs to be implemented too. But you can see here, we're dealing with the fact that we have a buffer and that we should buffer things out, and then when we're ready, call SIO to actually do the write request. So with all of that, we've gone through every single one except for special. And all special really does at this particular point in time is check to see if the particular XIO that we want to do is actually in our list. If not, send back a not implemented. And in fact, that should be a return. Otherwise, we take and do the appropriate SIO request based on the parameters that are set up. That is it. You want to add another XIO command. Let's say we want to add a buffer flush command. This one doesn't need anything. Let's call it 18. Then at that point, I would basically just call the CIO put flush. Something like that. You don't even have to go to the round trip for the CIO for that. Something to that effect. So that takes us through the majority of the CIO handler here. And you can see it here. You can see that it works, and you can see now basically where my headspace is and where things actually need to go. But also, you also see what it takes to actually implement a prototype of a CIO handler, and that it can be done in C and doesn't have to be done in assembler. So with that, I will leave you guys now until the next video. Have fun.